Okay, I'm back with question 21 from practice test 3. And this example wants us to combine the terms, if possible. We want to combine -9 cube root of 375 plus 10 cube root of 192. So combining with the operation of addition and subtraction means that we have to have like radicals, and like radicals will have the same index. These two have the same index of 3, but they also have to have like the number underneath the radical be alike as well. So you can see that these are not alike. So I'm going to try to simplify each one of these so that we can combine them together. So since these are cube roots, this index is a 3, so we have cube roots. I'm going to write down some perfect cubes. So we have 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed 343, I believe. Let me double check that one. My calculator. 343 and 8 cubed is 512. Okay, so you can see that the numbers underneath are radical. 375 and 192, neither one of them are perfect cubes. So I am going to try to factor 375 into a perfect cube and another number. So let's try to factor 375. So let's see what perfect square divides into 375. So I'm going to try 375 divided by 8. Nope, that doesn't go evenly. 375 divided by 27. Nope, that doesn't go evenly. How about 64? No. 125, yes. So 125 times 3 is 375. Okay, let's do the same thing with 192. Let's find a perfect square that a perfect cube that divides into 192. 192 divided by 8, that goes evenly. 8 times 24, but this perfect square is not big enough. I'm looking at the other factor, and there are perfect cube factors within that, so I'm going to go bigger. So does 27 go in there? No. Does 64 go in there? Yes. So 64 times 3 is what I want to do. So let's rewrite. I'm going to rewrite that cube root of 375 as 125 times 3. And I'm going to rewrite 192 as 64 times 3. So the cube root of 125 is 5, and I'm going to carry everything else down. The -9 gets carried down. Operation of multiplication gets carried down, and then the cube root of 3 gets carried down. The cube root of 64, we know that is 4. And then we still have the cube root of 3, and this is the operation of multiplication again. So we have multiplication. We're going to multiply to get -45 cube root of 3 plus 40 cube root of 3. And now you can see that we do have like radicals. They're the same index and the same number. So we're going to do the math on the coefficient. -45 plus 40 is going to give us a -5 cube root of 3. Okay, for number 22, we have write the 8th root of 31 in rational exponent notation. So what we know is that a radical is the same thing as a fractional exponent. So I'm going to give you the rule in general. If you have the nth root of a number, let's say b, we're going to be able to write that as b to the 1 over n power. And we can write this as well if we have the nth root of b to the m. This is the same thing as b to the m over n. So my example is the 8th root of 31. So in rational exponent, rational means fraction. In a fraction exponent notation, we're going to write the 8th root of 31 as 31 to the 1/8 power. These are equivalent to each other. So for number 23, we have multiply, then simplify completely. We're multiplying square root of 6 plus square root of 7 times square root of 6 plus 9 square root of 7. So we're going to multiply these together. And we are multiplying a binomial times a binomial. Let's use the FOIL method of multiplying. So we're going to multiply the first two terms together. These are the first two terms, so square root of 6 times square root of 6. We're going to multiply the outside two together. So that's going to be a plus square root of 6 times 9 square root of 7. Then we're going to multiply the insides together. These two are the insides, plus square root of 7 times square root of 6. And then we're going to multiply the last two together. So square root of 7 times 9 square root of 7. So when we multiply radicals together, we're going to multiply what's underneath them together. So these are both underneath the radical, underneath the square root. We can write that under 1 square root and do 6 times 6, that's 36. For the next term, we have square root of 6 times 9 square root of 7. We're going to multiply what's underneath the square roots together. 9 square root of 42. For the next term, we're going to multiply what's underneath the radicals together. We have square root of 42. And on the last one, again, multiplying what's underneath the radical. If there was a number in front here, we would multiply the numbers that are outside the radical together as well. So this is going to be 9 square root of 49. Now I can simplify some here. 36 is a perfect square, 49 is a perfect square, and then these two terms in the middle are like radicals, so we can combine them together. Square root of 36 is 6. For the like radicals, we do the math on the coefficient. So we have a coefficient of 9 here and a coefficient of 1 here. So it'll become 10 square root of 42. On the last term, square root of 49 is 7, so we multiply by 7. And this is 6 plus 10 square root of 42. 9 times 7 would be 63. Let's combine that with the 6. 63 and 6 is going to be 69 plus 10 square root of 42. And this is where we'll stop. It's very tempting to try to combine the 69 and the 10 together, but the 10 is attached to the square root of 42, and that makes these terms unlike. They are not like terms, and we can't combine them. For number 24, the directions say to rationalize the denominator. We have 11 over the square root of 11. So we rationalize when we have these fractions, and our goal is to make it so that there is no radical in the denominator. That's what rationalizing the denominator means. So in order to get rid of this radical, we need to simplify it. And we know that we can only simplify perfect squares or perfect numbers. So since this is a square root, we need to create a perfect square underneath the radical. So the perfect square that goes with 11, 11 squared is 121. That's 11 times 11 is 121. So what I'm going to do is I'm going to multiply by a form of 1 to create that 121 underneath the radical. So I'm going to multiply by square root of 11, and whatever I do to the denominator, I need to do the same thing to the numerator. Now multiply straight across. That gives me 11 square root of 11 over, now in the denominator, since they're both underneath the radicals, we can multiply them together. 11 times 11 is 121. And we know that the square root of 121 is 11. So you can see that we have gotten rid of the radical in the denominator, which is what we want to do with rationalizing. And one last thing is that we always want to write our fraction in lowest terms. You can see that the 11s cancel here, and we get square root of 11. So we rationalize the denominator. Okay, for question 25, we have solved the equation square root of x plus 17 minus 4 equals 3. Now when we solve this type of equation is a radical equation. What we do is we isolate the radical and then get rid of it. So isolating it first means we want to get it by itself. So we're going to add 4 to both sides, and we get square root of x plus 17 equals 7. We've isolated the square root, and now we have to get rid of it by doing the opposite operation. The opposite of a square root is an exponent of 2. So we're going to raise both sides to the second power. So both sides get squared. Now the operation of square rooting and squaring are opposites of each other, so they cancel each other out, and it's going to give me exactly what's underneath the radical. That's x plus 17. On the other side, we get that 49. And now that the radical is gone, we can solve this like one of our normal equations. So we're going to get x by itself. I'm going to subtract 17 and get x equals 32. Now one more step. Every time you solve these radical equations, you need to check to make sure that you get a true statement. So let's try it. We have the square root of 32 plus 17 minus 4 equals 3. 32 plus 17, that's 49. Square root of 49 is 7, and 7 minus 4 is 3. So we've got a true statement, so we're going to keep that solution of 32. So the checking step is not an optional step because sometimes you do get something that doesn't work in the original equation.